Hello all, as we continue to look at transformations and our use of matrices to either represent or apply transformations. As a quick review from part 1 from our previous video, we had this guide where we looked at we can represent reflections and dilations using matrices that look like this. Now, the new one that we haven't talked about at all, even in standard transformations, is if we reflect about the line y equals x. So that is, if we have some graph, we actually, instead of reflecting about the x-axis or the y-axis, we're flipping over this 45-degree line. That line there is y equals x. So reflecting about that. And what happens when we reflect about that is we're actually changing our x-coordinate to a y-coordinate, and we change our y-coordinate to an x-coordinate. That's the way we could think about how we can flip over the 45-degree line. So you want to keep that in mind, but the easiest way to think of it with this is we talked about top left being our x and bottom right being our y-coordinate, and we're doing something to each of those. When we're flipping them is we put ones in our secondary diagonal. So just want to make that clear because that'll be handy for a worked example coming up. But let's keep going. So previously we got up to here where we were reading off what are the transformations given in these matrices, and we're moving on to this stage where we're actually told a coordinate, we might call this coordinate 1, has been transformed, and this is coordinate 2 has also been transformed, and we want to find what the matrix is that does this transformation. So we're going with the concept that we have some transformation matrix A that we multiply by x, which is our old coordinate, and that gives us our new. So that is old, that is new. And in this case, what we're trying to find is actually A. We don't know what that is. We want to try and find that transformation matrix. So we're told, in this case, A, and now, we're told X and X dash, and same over here, we're told X and X dash. So we can put in placeholders, A, B, C, and D, in our transformation matrix, and we're doing now, fun, simultaneous equations with matrices. Okay, or it's sort of like simultaneous equations because we have two transformations when we're trying to figure out just one transformation matrix. So we can sub in A, B, C, and D for our transformation matrix, put in our first X and our X dash, and then perform the multiplication going down this way. And because of the 0 here, that gets rid of a whole bunch of it and collapses, and we just get AC is equal to 2, negative 3. So we know straight away from our transformation matrix that the A is 2 now, and the C is negative 3. We can do the same with the second point here. We don't even need to put the A and D in just yet. Because this has also got a nice 0 in it, which is making it handy. If it didn't have the 0 in it, then yes, we'd probably have to put this in here to be able to help us solve for B and D. But we put it in, same thing, perform the matrix multiplication, and we get B and D is 3, negative 1. So B gets substituted in as 3, and this gets negative 1. So we now have our transformation matrix, which is 2, 3, negative 1, negative 3. Okay. Now, the 2 and the negative 3 we could read off. We can read that that's a dilation of 2 from the y-axis. We can also read it's a dilation of 3 from the x-axis and a reflection in the x-axis. The negative 1 and the negative 3, though, they're a little bit weird. We're not just doing that basic dilation by 2 and the dilation by 3. It's a lot more complex, and it's not three-dimensional, but it is we're now not just applying one simple transformation and then one simple transformation. It's a whole bunch of transformations that are represented by this matrix. And then if I want to find, this question actually has a lot of parts in it, is it ends with asking find the image of -1, 7. So that's our new original. PowerPoint seems to have stopped working. Let's see if it comes back. But that -1, 7, there we go. That is our new x, our original x, and we're trying to find what is that transformed now that we've found a. So we have a, x, we do the matrix multiplication, and we end up getting, this would turn into 19, 4. So we can read that that coordinate has been transformed into 19, -4. Maybe a little hard to follow there with everything written down, so let's just jump straight into another worked example. In this case, it doesn't have the zeros in it, in either the starting or what it's transferred to. So we have x, it's gone to x dash, and we know, so we're going to let a equal to, at the moment, a, b, c, d, placeholders for our transformations. So we know that ax is equal to x dash, so we get b, c, d multiplied by, in this case, the original 2 will be equal to -4, 5. So let's do the matrix multiplication. So we multiply the first row by the first column, so we get 1a minus b equal to 5. And then we get c take away d equal to 5. So we get two equations there. So that's for transformation 1. Now we'll do transformation 2, which is this one. Same thing, we get our placeholders a, b, c, d, bracket. What do we start with? 3, 4, and that gave us 18, 5. Perform the matrix multiplication again, we end up with 3a plus 4b and 3c plus 4d, that is equal to 18 and 5. And we can read now, effectively we can read across the top row and then the second row. Same over here, we can read across the top row and the second row as equations. So from this first one, we can see that we've got a minus 2b is equal to -4. And from the matrix operation number 2, we've also got 3a plus 4b is equal to 18. So that's taking the first line of both of those, getting this set of simultaneous equations. And then if we take the second line from both of them, we get c minus 2d, 3c plus 4d. That one is equal to 5, and that one is equal to 5 as well. Okay. So now we just got two sets of simultaneous equations that we're just going to have to solve. We've got an a minus 2b, and then 3a plus 4b. We could do elimination or substitution. I'm going to rearrange this first one to get the a by itself, so we get a is equal to -4 plus 2b, and sub that in, sub in. So I'm left with 3 bracket -4 plus 2b plus the original 4b is equal to 18, -12 plus 6b plus 4b, 18. So I get 10b is equal to 30, so b is equal to 3. I'm going to sub that back in now. up here, so we get A is equal to -4 plus 2 by 3. A is equal to -4 plus 6. A is equal to 2. Okay, so I've got my A and B values from my transformation matrix from solving that set of simultaneous equations. Now I need to just solve this other one. So, same thing, I've got a C minus 2D, so I'm going to rearrange that. I get C is equal to 5 plus 2D. And I'm choosing to rearrange them because I've got a variable by itself. It's got a coefficient of 1, which means that it's then really easy to substitute. I'm then going to be able to substitute this back in. I get 3, 5 plus 2 plus the 4D is equal to 5. I get 15 plus D plus 5. Get 15 plus 10D 5. So I get 10D is 10. So D is equal to -1. I'm then going to now sub that back into this to get C. I get C is equal to 5 plus 2 by -1. C is equal to 3. So finally, using my A, B, C, D values, I get A was 2, B was 3, C was 3, 1. That is my transformation matrix that I called A at the start. So there's a bit there. There's a lot of algebra work, just doing the simultaneous equations, doing the matrix multiplication. That's it. So we can see that there is that matrix that can transform any coordinate. And if we were given, in this example B, in this case we're not given an example, but it could say find the transformation of, might give us some new point 3, maybe 2, 8. Well, then you would multiply the 2, 8 as a matrix by our transformation matrix, and that'll tell you its new position. We've got 2 more slides to look at. What have we got? We're 12 minutes in, so we can fit this in. Is sometimes we might be told 2 sets of transformations as separate matrix. We might have matrix A, that is one set of transformations, matrix B, that is a whole nother set of transformations. Maybe you were dealing with them individually, and then now you're told we need to deal with them together. Well, instead of doubling up on all your matrix, so you have your coordinate, multiply it by matrix A first, then multiply it by matrix B, we can actually combine those 2 matrices into a super matrix or just a combo matrix that combines those transformations, so that if we're having to use it multiple times, we can end up just multiplying by one's matrix instead. So where'd my pen go? So what I'm saying is we have some transformation matrix A, we might have another B. What we can do is we can combine these to get some new matrix, maybe call it C. And we can use this instead, especially if we're asked to use it multiple times. It's just being slightly more efficient in our work. Now, here's one of those fun things with matrices. If we have our first matrix, in this case A, and then our second matrix B, we actually have to multiply them together in the opposite order. So find the image of the point -2, 5 under the reflection of the y-axis, followed by, so we've got, this is our first transformation, and then followed by a dilation of factor 3 from the x-axis. So this is our second transformation. So what do we get? We can build A, that's quite easy, reflection of the y-axis, so that is changing the x-coordinate, that one, then dilating by a factor of 3 from the x-axis, so we change that 1 to 3 there. So let's put that together, so we get 1 is 0 is 3, and then 1, 1. So like I said, whatever the second transformation is, we actually list it first in this multiplication. So let's do this. We get 1, take the first row, multiply by the first column, the top left, we get 1, It's -1 plus 0. Then over here, first row by second column, so we get 0, 0. And down here we get 0 plus 0. And then here we're going to get first row by second column, get 0 and 3. So finally we get -1, 0, 3, which makes sense. If we think about it, reflecting the y-axis, well, the x-coordinate needs to be made negative, and we dilate by a factor of 3. So we could have intuitively put those together, but that's showing that that's where they come about. And that only works, though, if we change or put the order in reverse through the actual I need my brain to work. If we change the order of the actual matrices. Now we might be asked, and in this we're now saying find the image of the point -2, 5 under that transformation. Well, we know our transformation matrix is this. Multiplying that by, so this combo one we might call C, so we've got C by original point. So we now have, let's do this, -1 by 2 is 2, 0, oh yeah, 2 plus 0, and this one we get 0, 15, I get 2, 15, so this transformed is, and logically makes sense, 2, 15. The x-coordinate has been changed, been flipped, and the y-coordinate has been dilated by a factor of 3. Okay. Yeah, that's that. We might, no, we've got 2 minutes quickly. The last thing I want to add in is that we've looked at dilations and reflections at the moment. How do we bring in translations? Well, we actually added on as a separate matrix at the end. And I probably shouldn't have used C in the previous example, but this is our dilation and reflection transformation matrix, and then we actually tack on a 2x1 matrix here that is our translations. And it's pretty simple to read the translations in this matrix. Is the top is our x, and whatever we're doing to it. If we're going across to the right, well, it's +2. If we have a -3 in the bottom, well, then we're going down 3 on the y-axis. So we don't have to flip signs or anything. We read that intuitively. So I might leave it there, just to introduce that we can bring in translations there by doing a +C on the end. So just to bring this over, A is our dilation and reflection, and we're doing that to some coordinate. We're then adding on our translations, and that is going to tell us our new. Okay, so this is our old coordinate pair. This is our new. This will be our dilations and reflections. And this will now be our translations. Okay. A is a 2x2 matrix. C is a 2x1. Then you can do the operations that are there on the screen, and then you end up with a dash representation of a transformation. You can read off what they are. In this case, this is a really odd one, that we have y dash or x is equal to y dash plus 3. Why is there a y in the x, and same over here, why is there an x dash in the y equation? It's because in this example we're told we're reflecting through the line of y equals x, so we're swapping every y coordinate for x, we're swapping every x coordinate for y. But yeah, that's it for now. If you have any questions, please put them below or ask in class.